Hi, everyone. This is going to be the first part of your week one online learning experience. I'm going to talk a little bit about thermochemistry, thermodynamics here. These notes are in the folder for thermochemistry and kinetics. So you can get those there. I'm going to write up a little something where you can see what you should be doing this week, and that'll be there every week. So we'll start just with some vocabulary terms. We've got energy, the capacity to do work or produce heat. Heat, which is going to be, the unit is going to be a Q. And I usually do a cursive Q for heat. Energy that's transferred from one object to another due to a temperature difference. Heat is measured in joules or calories. So these are not the calories that you eat. They are different. We eat big C calories, which are different than the small c calories. You're going to see joules the most, and you're also going to see kilojoules, which would be lowercase k, capital J. So temperature is not the same as heat. Temperature is proportional to the average kinetic energy. We talked about that when we talked about our gas laws. An intensive property, an extensive property, we've talked about these at the very beginning of the year. An intensive property doesn't matter the amount that's involved, where an extensive property relies upon mass or volume. So an intensive property, where it doesn't matter the amount involved, that one is going to be temperature. It doesn't matter if I have 1 gram or 100 grams, I'm going to have the same temperature. But an extensive property relies upon the mass, and that's going to be heat. Heat doesn't matter on how much you have. So we've got specific heat, the quantity of heat needed to raise 1 gram of water by 1 degree Celsius. And so specific heat is going to be a capital C. And it's going to be heat over mass times the change in temperature. And our units are almost always going to be joules over grams degrees Celsius for our specific heat. Now you'll notice that specific heat for water is 4.184. This is a very important number, and it's going to be used a lot in this unit. You don't have to memorize it, but you'll use it so much that you'll end up remembering it. And that's the temperature, and that is the specific heat for water, which is very high for a small molecule. Now, water's high specific heat is one of the reasons why we're able to live on this planet. The sun cannot immediately evaporate all of the water on the planet because of its high specific heat. And so we have weather and rain, and we have the oceans and all that stuff that we need in order to survive. I'm going to put a link on the page in the write-up that I'm going to do for this demonstration for the burning dollar, and it demonstrates water's high specific heat. A good example of a specific heat, let's think about going to the pool on a hot day. You go and you set your stuff down on the chair and you sit down and it like burns your leg. Then you go walk into the pool and the water is kind of cool or cold. And that's because it takes way more energy to heat up the water than it does the metal on the chair. And that's why the metal feels hot and then the water doesn't. So metals usually have a very low specific heat. And we will see some of those examples with that. So calculating heat transfer. So how do I do these calculations? So heat transfer Q. So remember, Q is the heat. M is mass. Q we know is heat. M is mass. C we know is the specific heat. And delta T is the change in temperature. And so calculating heat transfer, Q equals MC delta T. A lot of people say MCAT to remember. To do delta T, it's always the final temperature minus the initial temperature. Okay, so we don't want to forget we're doing final minus initial always, because the sign matters. We'll talk about that in a second. So it says calculate the heat in joules needed to warm 10 milliliters of water from 0 degrees Celsius to 37 degrees Celsius. The density of water is 1 gram per milliliter. So delta T, definitely want in degrees Celsius due to our specific heat. Remember the C for water is 4.184 joules over grams degrees Celsius. We are using degrees Celsius, no more Kelvin like we were doing in gas laws. And then the one thing, mass is in grams, obviously. 10 milliliters is 10 grams due to water's density. So just quickly, Q equals 10.0 grams times 4.184 joules over grams degrees Celsius times 37 minus 0, which is 37 degrees Celsius. Put that into your calculator, and your Q will be, with sig figs, 1,500 joules, because 37 has 2 sig figs. What would that be in kilojoules, which is a more common unit? So we just take 1,500 joules, joules on the bottom, kilojoules on top. And that's going to be 1.5 kilojoules, still keeping those sig figs. So MCAT, pretty simple. Enthalpy, which is represented with an H, is the measure of heat content at a constant pressure. We are always at a constant pressure whenever we're in a room. We cannot change the pressure of an entire room, so we can always use this term. So Q and H can be interchangeable when we're talking about heat calculations. So Q equals MC delta T, delta H equals MC delta T, same thing. Super important. I said those signs are very important. They tell us a lot. Delta H is positive, it's endothermic. Delta H is negative, it's exothermic. We must remember that. If you do not remember that, you're going to have a terrible time with this. So there are different enthalpies that we'll come back to. I'm not going to read these to you because you are more than capable of reading yourself. So we've got enthalpy of reaction, enthalpy of combustion, enthalpy of formation, enthalpy of neutralization, enthalpy of vaporization, and enthalpy of fusion. And we will see most of these again. So this is going to be the last slide for this part of this week's assignment. So we calculated enthalpy change, so Q equals MC delta T. Now we're going to see how much energy is required or given off in order to change the state. So heat is transferred when there is a difference in temperature, as we saw in the previous equation, but we must also take into consideration the heat when we are going through a phase change. So we can have molar heat of fusion or molar heat of vaporization. So fusion, which is different, is going to be melting. And vaporization is obviously vaporizing. So fusion, the energy required to melt 1 mole of a solid. The delta H for fusion is going to be positive 6.02 kilojoules per mole. Molar heat of vaporization is going to be positive 40.6 kilojoules per mole. It takes way more energy to turn the liquid into a gas than the solid into a liquid, and that should make sense to you because the gas molecules are moving so much faster than the liquid, but going from a solid to a liquid isn't that much of a difference. Now the next question, which is a good one, what would be the molar heat of freezing and the molar heat of condensation? When we're talking about heat transfers, it all depends on where the heat's going. Is it going in or is it coming out? When you melt and when you vaporize something, you are putting energy in. That is why it's endothermic and it's positive. So for freezing and for condensing, that's going to be an exothermic process. And so it's going to be the same value, but negative. So the delta H of freezing is going to be negative 6.02 kilojoules per mole. And the delta H, so the enthalpy of condensation, is going to be negative 40.6 kilojoules per mole. It's all about the direction in which the energy is going. So sometimes you can see it in kilojoules per mole. Sometimes it could be joules per gram. You just have to pay attention to what your units are and make sure that they match up in order for you to get your answer. So it says calculate the heat needed to change 100 grams of H2O at a liquid, so water, at 100 degrees Celsius to steam. So we're just doing a phase change. The temperature is not changing. We're just doing a phase change. So we know so we're going to steam. So that means we're going to do the enthalpy of vaporization. So that's going to be 40.6 kilojoules per mole. I've got 100 grams. So what I'm going to do is I'm going to put a decimal there so it's 3 sig figs instead of 1. Just quickly turn it into moles. And that's going to give me, oh, what is it going to give me? Let me get a calculator. I did 1 sig fig and now I'm changing it. 100 divided by 18.01. It's going to be 5.55 moles. So to calculate the heat needed to change it, I'm going to just do delta H is equal to, well, no, let's not do delta H. Let's keep it Q just so we're all doing the same thing. Q equals, so N, the number of moles, 5.55 moles multiplied by the 40.6 kilojoules per mole. And plug that into my calculator. That should give me, with the correct number of sig figs, 225 kilojoules. And that's how you calculate the energy for a phase change. In the next part of these notes for this week, we're going to look at throwing all those together and looking at something called a heating curve and another way to calculate delta H, a couple other ways. So if you have any questions, feel free to reach out. Look at the Word document for this week, part 1, to see what the assignment is in the homework packet. Yeah, so stay tuned for the next part.